Hello, if you read the description that's available on the Flat Earth Sun, Moon, and Zodiac Flat Earth Clock app that David Weiss has developed, one of the first sentences in the description says that it shows you where you are and where the sun and the moon are on their journey around the face of the earth as shown on the azimuthal equidistant map. You can see where the daylight and nighttime are, as well as the position and phase of the moon as the sun slowly laps it every month. I've already covered some of the other peripheral stuff around the app and what I thought of them, but I thought that I was going to tackle what in my mind is the centerpiece of the app itself, which is to somehow convince the user that the sun and the moon just simply circle above a flat earth as described in this application description. So one of the first things that I noticed when I got the app and I started to play around with it was that the moon always remains on the equator and never seems to move from tropic to tropic as we can see in real life. I've made a video recently on the lunar analemma. As you can see, the dark blue dots over the sky background kind of appear like a teardrop. And what I've noticed was that as the days and the months progress, that teardrop changes shape, and at one point, instead of pointing up like this, it'll point down. But I have 3 years of video camera footage that shows that at the height of summer, the full moon is at the bottom of the image, and in winter, the full moon is at the top of the image. The only time that the full moon would appear along the celestial equator, which would represent when the moon is directly above our equator, would be around either of the two equinoxes. So it would be either in March or in September. Throughout the rest of the year, the full moon is going to be either above or below this red line here. That was the first major discrepancy that I found in his Flat Earth Clock app. Second thing that I noticed was when I used the little speed controller to advance it at non-real-time speed, every time that midnight would come around, the moon would jump roughly 7%. And if I kept looking at the animation, I would notice that there would be some days it seemed to overshoot the previous day, and so it would stay at that same displayed moon phase. So given what I've seen, I was trying to analyze how they could have gone about accomplishing that. And one of the first things that I thought of was that they would somehow have extracted a large collection of moon phases along with their dates. As the time and the date would have approached, they would have found the appropriate entry, and then they would have been able to say the last full moon would have been on June 28th and we're now July 5th, so therefore it should be somewhere around 42%. That's what I initially thought, and I kept doing some more analysis, and I've come to the realization that they probably implemented a different algorithm to determine the phase of the moon. But I needed to find out what the exact cycle of the moon in the app was. So what I did was I ended up choosing noon, and I don't know if I covered this in very great detail in any of my previous videos, but when you choose the slow fast speed, the time and the date on the top left are updated to match the time and the date on the clock hands, and that midnight rolls around when all the needles pass the 24-hour marker. If I choose the even faster speed, what I've noticed was when I choose the faster of the two time-lapse speeds, whenever I click on that, whatever the current time is when I click that, that becomes the midnight hour marker. I've also noticed that the needles have absolutely no effect, and that the only thing that can be reasonably relied on is the hour hand. And so if this was the time when I clicked on that, so if I happened to click on this at 9:06 a.m., then every time that that needle would go around past 9:06 a.m., that is when the date would change at that high speed. And so the reason reason why it shows 9:06 a.m. is that is the 12-hour marker past the midnight marker on my animation. So in other words, when I made this screen recording, I started it at about 9:10 p.m. So I figured that when the hour hand moves past that point and the day changes, if I go a full exact 12 hours beyond that, I would have the middle of that day's cycle. So it would be somewhere around 46.5, 47% or thereabouts. So I built a spreadsheet starting from the first full day's animation. This would be at around noon. I went and grabbed the displayed moon phase, so 42 to 50%. So it would be waxing in this case. And I did that for every day for the following year, and I was specifically looking for certain patterns. So in this case, on July 5th, I had 42 to 50. If I go to the next day, July 6th, I have 50 to 57. Go ahead the next day after that, I've got 57 to 64, 64 to 71, so on and so forth. So that's what I wrote down here. And as we can see here, on the 17th, we have a duplicate moon phase. So July 10th, 78 to 85, July 11th, 85 to 92, July 12th, 92 to 100, July 13th, 92 to 100, July 14, 100 to 92. I was noticing some rather odd patterns in the way that this flat earth clock was calculating the phase of the moon and also displaying it. If you paid attention to some of the animations, particularly the 24/365 animation video, you'll notice at the bottom left that I have an indication of the moon's illumination. And full disclosure, in researching how David Weiss implemented his moon phase in his app, I noticed that I was forgetting to account for the sinusoidal nature of the moon's illumination when it should be the percentage of the moon's orbit. So for example, when I was saying that it was at 85% illumination, it was really 85% of the orbit. I had implemented that because I wanted to get that video out as quickly as possible, and I didn't spend enough time making sure that it was 100% accurate. So I ended up using my computed moon phase with David Weiss's displayed flat Earth moon phase, and I ended up making a few different graphs. In this case, what I ended up doing was I calculated the change in the percentage of the full moon. So in this case, I ended up calculating the change in the moon's monthly orbit every day for the year, how David Weiss calculated it versus how I calculated it. And so this is expressed as a ratio between 0 and 1. 1 being a full month's worth of rotation, and by dividing that into every single day, we should arrive at the moon's synodic period of about 29.53 days. So as we can see, that there are some days it jumps ahead a little bit faster than others, and there are individual days where he doesn't advance the moon at all. In contrast, when we compare how I calculated it, I'm using the daily delta, and I've got quite a few more decimal places, so that's why it looks more sinusoidal. And here I was doing a few more graphs as well, comparing the two. And from what I could see in my analysis, there wasn't enough granularity in how he displayed his values to be able to determine whether he was using or accounting for the moon's eccentricity and how the moon speeds up and slows down in its orbit. In fact, it's the way that the moon speeds up and slows down that creates that analemma in the sky. One of the things that I did notice whenever I was entering all the values in, I ended up seeing what appears to be a simple 28-day cycle set of labels repeated again and again, and depending on how he calculates the moon phase, that's why he either repeats or he doesn't repeat a particular label. And I noticed what appears to be two separate typos in his displayed labels. So whatever lunar phase he ends up calculating, he goes and uses a lookup table to find out what value to display. In the case of the waning moon, it starts off at 100%, decreases by 8 to 92, then from 92 to 85, 85 to 78, 78 to 71, and then rather than go 71 to 64, it looks like whoever coded it did a typo and it now displays 71 to 74, but the next day it jumps down to 64 to 57. The other typo appears what should be, to me, 7% waning to 1% waxing, so that the next day it starts off at 1% and goes up to 7. So it looks like he's got two typos in his labels. So now that I had an overall layout for how he might have gone and implemented it, I tried to find out exactly how he might have done it. And in researching how to calculate the phases of the moon, I found different algorithms to do that, and they're fairly simple. What you do is you end up calculating the date difference in seconds from some full moon, and different algorithms will use different full moon dates. This one uses January 1st, 2001. There is another one that I found that uses a date in 2000. So from there, it calculates the number of seconds that have elapsed from that particular time so that they can then subtract that time from the current time, and that gives you a difference in seconds from that full moon to the present. After calculating the number of seconds, what this specific algorithm does is it converts it into days by dividing it by 86,400 seconds, and that will give you days and fractions of a day. From there, it can calculate the number of lunations, which are basically going to say that in the time that has elapsed, there were 47.653 lunar cycles, for example. And in most of these algorithms, they don't really care about the whole number, they're only interested in the fraction, so they drop the whole number and they'll look at the fraction, and then from there, between 0 and 1 will represent the moon's orbit around the Earth from full moon to full moon. And then from there, it's able to calculate the moon's phase and give a rough percentage. So as you can see, what I did here was I based it on a similar principle. The last full moon that occurred was June 28th of this year. And based on July 5th, I calculated the number of days. And to simulate what David Weiss did in his app, I just rounded it up to a whole number. But what I tried to do is I tried to play around with different values to see if I could match as many days as I could. And while I was able to get some days, I think the best I was able to get was up to the first 40 some days. So probably right around here. By playing around with some of these offsets, what's the exact number of days per month? What's the shift? And the shift could be within the second or even a fraction of a second, because I'm just dealing with fractions, an overall shift. And I was trying to play around with some of these numbers to see if I could ultimately reverse engineer the way he calculates the lunar phase. So the best I was able to get was the first 40 some days, and then after that I would get some days that weren't exact. So in this case here, this one here should have repeated at 78 to 71, like that there. And so in this case, I'm forever dancing on the edge of a transition between 2 days, and so I can't get an exact match. But I have a sneaky suspicion that whatever algorithm he uses to calculate the phase of the moon is based on something similar to that. Also, given the fact that he renders the moon always over the equator like that, also helps to solidify my suspicions that he's not really using an algorithm to calculate the moon's phase or position so much as using a simple algorithm to calculate the moon's phase. So if we come back to this, does the flat Earth, sun, and moon clock correctly depict the moon's phase and position over the flat Earth? Whatever algorithm you choose, In order for that statement to be true, the moon would have to cycle back and forth between the two tropics every month. And because it doesn't, I would have to say that the description in this app is incorrect and that the Flat Earth Clock app fails to correctly show that. So that's what I found with the moon. There's going to be a whole lot more to come. I'm probably going to be looking at the sun's movement next. Thank you for watching. If you like the video, I would appreciate the thumbs up, the subscribe if you're not already, comment below, do the whole sharing bit and do Google's work for them. And with that, I'm going to see you again in another video soon enough. So bye for now.